So we're very happy to have Dr. Mina Tahmasbi Arashloo. She's Canada Research Chair in Minimizing Human Error in Modern Networks and an assistant professor in the School of Computer Science at the University of Waterloo. Her research focuses on programmable computer networks, specifically in designing and developing automated process program to program and reason of modern networks. In doing so, she brings in techniques from other computer science disciplines such as programmatics, programming languages, and hardware design. She's a postdoctoral fellow at Cornell, received her PhD at Princeton, and she's been named the Rising Star in Networking and Communications by N2 in 2021, and her work has been recognized by the ACM SIGCOM Doctoral Dissertation Award and the Microsoft Research Dissertation Grant. So, without further ado, please, the floor is yours.
Thanks, Curtis, for the introduction. Can everybody hear me? My voice is not that loud.
Yeah, I want to bring it a little bit closer.
Yeah.
Okay.
How about now?
Is this okay?
No.
No? Do you want to use this one or?
I'll just
It's just this one.
Okay. All right, well, thanks for the introduction and thanks for having me here today. I'm very happy to tell you about some of the work that we've been doing on trying to automatically and proactively reason about network performance. So first, there we go. First, I want to start by just talking a little bit about how online services depend on networks and require them to kind of give them good performance. So a lot of the online services that we love and use on a daily basis, they rely on computer networks to help them exchange data between different computers. So for example, when a server on Google Data Center is returning the result of a search question that you've had, or a server that is kind of posting YouTube videos is giving you data for the next few seconds of the video that you're watching, they'll have to break this data up into smaller units called packets, which are the unit of transmission over a network. And these packets are going to traverse a series of devices called routers to get to the destination, which would be the client, that would be you, so that the data can be displayed to you. So these online services, they do depend on computer networks to do this data transfer for them. But that's not enough. They actually want the computer networks to do this data transfer well. And what that means is there are certain requirements in terms of the latency, throughput, jitter, and data loss that can happen during this transfer. So for example, one of the important performance metrics that applications usually require of networks is to keep the data transfer latency below a certain threshold, let's say X. And this X can differ between different applications, but it's usually a very important metric because if the data transfer latency is high, your search results are not going to come back as fast, or your video is going to take longer to load. Another important metric that usually comes up is data transfer throughput or rate, because let's say you're, again, not with search that is just a few data packets, but with something like video where you're kind of continuously expecting some data to kind of show up on your screen at a certain rate. You would expect the network to be able to keep up with the data transfer rate kind of at that rate from the server to your client. So in that case, data transfer throughput being above a certain threshold also matters for kind of certain applications. And there are other metrics like jitter and loss that many applications care about and expect the network to provide kind of certain guarantees for. Guarantees a strong word. I just try to kind of provide that kind of certain good performance within certain tasks. And do please stop me at any point in time if you have questions about. So online services, as I mentioned, they depend on the network to provide good performance, but that's not really an easy thing for a network to do, because the network is a shared infrastructure. So most of the time, there are many traffic streams that are using the network all at the same time, which means they would be more often than not competing for shared network resources. So one example of that is kind of the router that I've circled here on the screen. So this router has 4 links, 2 of them to the 2 servers that are, let's say, hosting Google Search and hosting YouTube, and 2 more going to the other routers in the network. And there could be situations, right, like this particular example here, where you can have two traffic streams coming in from two different links that want to go out of the same link. So in this case, this device is receiving traffic at a higher rate than it can actually send out, which means temporarily there's going to be some data packets that have nowhere to go, so the device has to store them until it is their turn to go out. So for that reason, most of our devices, right before each link, they have these packet buffers or packet queues that are supposed to keep this temporarily keep packets when situations like this happen, so the packets can wait there before they can be sent. So you might be wondering, how does this actually affect the performance metrics that we talked about? Well, if packets have to wait in these queues, that means they're going to take longer to get out of the device and go to the next hop and get to their destination. So that would mean that data transfer latency is going to get increased. And in extreme cases, these kind of packet queues might actually fill up. So there might possess finite memory. So there might not be actually any place to store an incoming packet, and then the packet is going to be dropped, and that could cause packet loss and decreased throughput. If the queue size kind of fluctuates, then the data transfer latency is going to fluctuate too, so you'll have jitter. So how these buffers behave and how they build up when contention happens is actually going to directly affect the performance metrics of the network, which is going to affect the online services. All right, so what network operators want to do is to prevent that from happening as much as possible, and when they happen, to manage it effectively. So what are the tools that they have to be able to do that? There are a number of algorithms and protocols that network operators have to decide for their network, and those would affect how these queues build up and when contention happens, how it is managed. One set of algorithms that are important are kind of running at the endpoints and then decide how fast data should enter the network in the first place. So these are congestion control algorithms. And how these would affect kind of this whole buffer build-up situation that I was talking about is, depending on how fast kind of different endpoints are sending data into the network, it kind of determines how much of what percentage of the buffer each of these traffic streams is going to occupy. So for example, video traffic usually has a lot more data to send than something like search that is only kind of a few packets back and forth. So if you just let video traffic to send traffic as fast as it wants into the network, then when it's kind of competing with search traffic, it is going to fill up most of the buffer, which would not leave a lot of kind of space for the search traffic, which could affect the search application and network performance that a search application experiences in a negative way. Another set of important algorithms that can affect this buffer buildup is routing protocols, which are the ones that decide which paths the packets should take going from sources to destinations. And the way that can affect queue buildup is that actually determines which flows are going to share some resources and are going to share some buffer and content for resources. Because, for example, in this case, if you would have chosen paths instead that, for the green path to go kind of this works great. To go over here instead of going over the top, and the orange and the green traffic would not have even intersected at all. So they would not even contend or compete, and none of them would experience any performance problems. And last but not least, even if you kind of pick the best congestion control algorithms, the best routing algorithms, contention is going to happen at some point. That's why kind of buffers exist in the network. So once it happens, there are certain protocols and algorithms that run at that contention point, like a packet scheduler, that determine out of everybody that is in the buffer, which packet gets to go first. And again, here, the choice of the algorithm is going to affect the order at which packets exit a queue once the queue has already built up. And you can imagine that, your choice here matters if it's just first in, first out. Again, video traffic that has more packets can overwhelm the search traffic, whereas you can instead prioritize search traffic whenever the contention happens over video traffic. All right, so hopefully at this point I've convinced you that what algorithms we pick or network operators pick in these situations affect the performance, the performance metrics that we talked about, like latency and throughput for different applications. So network operators want to make sure that they pick the right ones. And now I think the question that I'm going to focus on for the rest of the talk and what we've been trying to work on is how do I actually know if I have picked the right algorithm or protocol for my network? Specifically, we want to help network operators to answer this question. If I deploy a certain algorithm or protocol, will my network ever experience poor performance? Will there be ever a situation where the latency goes above a certain threshold or the throughput drops below a certain threshold? So how do people do it today? How do network operators answer this question for themselves today? There are two kind of sets of approaches. One kind of approach is empirical, right? You prototype the algorithm or protocol that you're interested in a simulator or an emulator or a testbed. And then you pick a packet trace. So this would be the sequence of packets that presumably you assume applications are sending into your network. And then you try your algorithm on that input trace and see if it is doing what you want it to do. The problem here is that you can only do this a certain number of times, right? This is a simulation or an emulation, it's an experiment. So you're going to have to pick, there's like a finite number of traces you can pick to actually try. So it's important that you pick the right ones. And more often than not, this set of traces that you can actually try is much smaller than the all possible packet sequences that can go into your network. So more often than not, you're going to miss something that might happen once you deploy the algorithm, and then that will cause a problem. So that's with the empirical approaches. For the analytical approaches, there have been some analytical approaches, based on queuing theory and network calculus, where they can help you find some bounds on these metrics. So if you manage to approximate the algorithms in the network and the kind of input that can enter the network with some kind of very well-defined and well-behaved functions, these works have some calculus and some theorems that can help you figure out some bounds on the kind of latency or throughput that your network is going to experience. Which is great in the sense that doesn't have the problems that empirical approaches have, but it's still very restricted because the functions have to really be approximated. The functions that you have to approximate your algorithm with have to be very well behaved. To work with that calculus, it is actually difficult to extend them to kind of new network functionality or more kind of new traffic patterns that might happen in a network. So if you change the algorithm a little bit, then you have to kind of find another function that approximates it well and to be able to plug it in and get the bounds that you want. Any questions so far? Right, so what we are proposing instead is to use logic-based formal methods for network performance analysis. And this is based off what I'm going to present for the most part of this talk is based off a paper from now about 2 years ago. And the only reason I put kind of logic-based there is to kind of make a distinction between calculus. So as I'll go through the talk, we're kind of mostly trying to model a network in logical formulas and constraints as opposed to kind of a calculus-like model. All right, so how does that work at kind of very high level? So very high level, what we're going to do is we're going to create a model of our network with some logical variables and constraints. So it would be a kind of a conjunction of a set of logical formulas. And then we'll have the operator give us the property that they're interested in. So in our setting, that property is going to be something like, can the latency for this particular application go above a certain threshold? Or can the throughput of data transfer for this particular application drop below a certain threshold? And then the model and this property are going to be fed into an analysis tool that can automatically analyze the entire input space. And what I mean by input space is that it can kind of look at all possible values that can be assigned to the free variables in these logical formulas and see if there is any situation where that property is going to get violated. And in our case, the free variables are the packets that are coming into the network. So basically what we're trying to do is to kind of look at all possible and use these tools to look at all possible packet sequences that can come into the network and see if there is any situation where the property that we're interested in is going to be violated. And these tools that we kind of reuse a lot and kind of modify a little bit from formal methods, programming languages, language community, help us figure out if this property is always going to hold, or give us a counterexample that says, here's a particular input particular packet sequence that is going to violate this property that we were interested in. All right, so how is this better than the two previous approaches that I just mentioned? Compared to empirical approaches, it is automatically analyzing the entire input space. The all possible packet sequences that can come into the network. Compared to the empirical approach where you had to just pick a finite number of, a small and finite number of packet traces to try out. So it provides more coverage. Compared to kind of the existing analytical approaches like queuing theory and network calculus, as long as you can model your network and your property in first order logic, you can technically apply this kind of approach to the problem, which means it's a little bit more flexible and more easily applicable and modifiable as new kind of network functionality and traffic patterns. All right, before moving on, I'm going to dive into kind of these four boxes throughout the talk. But I just wanted to point out we're not the first to kind of try to use formal methods to analyze networks. Network verification has been an active area of research for the past 10, 15 years. What kind of distinguishes our work from prior work in this area is that most prior work focused on analyzing functional correctness. Because the network's main functionality is to actually get data from point A to point B. So there's a lot of work on analyzing properties related to connectivity and does the data transfer actually happen correctly across the network. Whereas in our case, we're kind of focusing on performance-related properties, again, throughput, latency, etc. All right, so diving into these kind of four boxes, the first kind of step that we have to take was to find what is the best way to model our network using kind of in logic. And the main challenge here was to kind of figure out what is important to model, because if you model every single detail, so you technically can create variables for any point of uncertainty in your network and constraints to kind of capture how they interact with each other. But if you model every single detail, then kind of the tools that can analyze these formulas, their analysis time grows exponentially most of the time when the number of variables and constraints grow. So you want to make sure that you pick what matters to model in terms of the property that you're interested in. So to motivate a little bit how we picked our model, I want to go back to this kind of route. Oh, I have to right here, to this router that we've been talking about. So here is just kind of a zoomed in view of inside of a router. It has like a generic router has multiple links or ports. So outside where kind of traffic can come in and traffic can come out. And it usually has a table called a forwarding table that provides a mapping between destinations and ports. So when a packet comes in, it looks at the address, the destination address that is inside the packet, consults the table, and figures out which port that packet has to exit from. And as we saw at the beginning of the talk, right, once the output port is decided, there could be situations where packets coming in from multiple ports want to go out of the same output port. So usually behind every output port, there's a bunch of queues that are going to hold packets temporarily until it is their time. To go out. And most of the time, performance problems happen when there's contention, and when there's contention, there's going to be these queues that are holding packets. So this is an important part that we had to include in our model. So we had to include queues and model them in our model. The second thing I will point out here is that in terms of the input coming into the network, right? We couldn't just kind of model a single packet and how it would traverse the network, because again, we're trying to kind of model performance problems, and whenever there's contention, there's more than one packet involved. So it's important to actually model the input as a sequence of packets that can come in from different locations or different ports, and also the time at which they enter, because that's the way we can kind of try to model how they interact and whether they're going to end up in the same queue at the same time, and how these queues are going to build up. So with that, I'm going to go into a little bit more detail about kind of our formal model of the network in this work. We're modeling the network as a composition of queuing modules. Where a queuing module, just our building block, is just something that has a number of input queues and a number of output queues, and some processing logic in the middle that takes packets from input, processes them, and pushes them to output. And we model this over kind of some discrete time. So every time step, this queuing module is going to take packets from the input, do some processing, push them to the output, and then we go into the next time step. And then the processing module, so you can imagine, right, this can at least model some part of a router, kind of a subset of queues in a router. And to build up a bigger network, you can compose these queuing modules together. And composition is kind of quite natural because you can feed the output of one module into the input queue of another module. So you can very naturally compose them together to build a model of the bigger network. So how does this, so I mentioned you're modeling this as logical formula, so I just want to very quickly talk about how that happens. So we actually kind of explicitly model everything. So for every queue, we keep a bunch of elements, and we kick off a bunch of variables that keep track of whether there's a packet or not in each element of the queue at each point in time. And as I mentioned, we're kind of modeling the network for a sequence of time steps. So for each time step, for each element of the queue, we have a variable that represents whether there's a packet there or not, and some attributes about that packet, for example, what traffic class it belongs to. Then in terms of kind of our inputs, I talked about kind of packet sequences that come in. So we have variables that represent, we have a bound on at most k packets can kind of enter a network in each time step, and then we have variables that say what is the ith packet that wants to enter a queue at a certain point in time. And again, for each queue, we also have a variable that kind of captures how many packets are going to be dequeued from it at that time step. And then like if you're kind of modeling this for 15 time steps, there are 15 sets of these variables for each queue. Now we also have a bunch of constraints here. So one set of constraints for each queue, again, kind of captures how the elements in each queue are going to change from one step to the next based on the packets that came in, based on the in-queue variables, and the packets that went out based on the dequeue count variable. And we also have constraints to kind of capture the processing logic in the middle, which is going to determine at each time step how many packets are going to get dequeued from each input queue. So it will kind of have constraints to determine the value of the dequeue count variables and what packets should go into the output queues of this module. So it will determine the value of the in-queue variables for the output queues. All right, so I did mention at the beginning that we want to make sure that we only model things that matter. And I think for us, we decided to focus on queues and it's kind of input packet sequences. Still, this can blow up because, like, I don't know, for each queue, we're modeling every element very precisely at every time step. So it is, if you kind of do it naively, it does blow up, and it did for us. So we did a bunch of optimizations that I won't get into. Or if you're interested in, I can talk more about that to make sure that, at least we can analyze this set of formulas for a bounded number of time steps that went up to kind of 15 or 16 rather efficiently. All right, so that was kind of the first component, figuring out how we're going to model the behavior of the network. So the model we ended up with was a composition of these queuing modules. And again, they're kind of captured using logical formulas. Now, the second step is kind of specifying the property that we're interested in to analyze on this model. So again, going back to the beginning of the talk, our focus is entirely on queues because what we realize is when performance problems happen, queues are at the heart of it. So the properties are also defined in terms of queues. So an operator could say, for this particular queue in the network, here's a metric that matters to me. It could be the queue size. It could be the total number of packets that have entered that queue. It could be the rate that packets have entered that queue. That's the inter-arrival kind of gap between packets that have entered that queue, or any other metric that they're interested in. It just has to be around the centered around the queue, some metric about the queue. And then they can kind of express their queries in terms of what are acceptable values for that metric. So for example, they can say for this Q1, I want to make sure that inter-packet gap or the arrival rate of packets into this queue is greater than a certain threshold. If the inter-packet gap is greater than a threshold, it means the rate is less than 0. That's okay. Or they can compare kind of the same metric between two queues. So they might want to say, I want to make sure that the queue size of this Q1 is always less than the queue size of this Q2 at this particular time. Or they can aggregate a certain metric over a bunch of queues and then ask questions about that. So it might matter to them that the total number of packets that enter this kind of set of queues should always be greater than 1. So to sum up, all the properties are also specified around queues. Some metric over the queue, and you can either compare it to a threshold, compare it to the queue, metrics for two queues together, or kind of aggregate metrics across the queues. All right. So that's for the kind of specifying the desired property. Now we had our composition of queuing modules in terms of some formulas, which we're calling the model, and the property in terms of a formula that we're representing by property here. So what we want to find out is if model the conjunction of model and the negation of property is satisfiable or not. What does it mean if it is satisfiable? If it is satisfiable, it means there is an assignment to the variables here. And remember, our free variables were the input packet sequences that are coming into the network. It means that there is an assignment to the variables, so there is a packet sequence that can come in and violate the property. And if it is unsatisfiable, it means no matter what packet sequence enters the network, then the property is never going to be violated. So once we construct this formula model conjuncted with the negation of the property, we use an SMT solver called Z3 that can take this formula and tell us whether it's satisfiable or not. And if you're kind of familiar with formal methods literature, that's basically bounded model checking with this SMT solver called Z3. And the reason it's called bounded is because we only do it for a certain number of time steps, which kind of empirically, it couldn't go beyond 15. It kind of stayed around 15. All right. So now this last part, you might think that we're done. Great, we kind of gave this formula to this solver. It either tells us that this is unsatisfiable, so the property is always going to hold, or it's going to give us a specific example that shows us where this property is not going to hold. So I'm going to focus on this for a bit, because this is something that we realize is kind of not necessarily an informative output to provide to a network operator. Because remember, we're trying to kind of help a network operator understand whether they have picked the right algorithm or not. So here's an example to show you why we thought this might not, like just outputting a single counterexample might not be an informative output. So let's say we have a priority packet scheduler, which it has 4 input queues: F1, F2, F3, and F4. And F1 is the highest priority, and as we kind of go down, the priority decreases. And all of the packets that come into all of these queues, they want to go out of this output queue. So this priority scheduler is mediating between them. And it's very simple, strict priority scheduler. So if there's anything on the highest priority queue, it will send that one out. Otherwise, it goes down one queue, then one queue, then another queue. So suppose that, it's a very simple example, but for the sake of the example, suppose that the operator wants to know if F3 is ever going to get blocked for some consecutive number of time steps. So it has some packets to send, but the scheduler doesn't pick it to send. So we can model this in our, as a queuing module in FPerf. FPerf is our tool. And we can also kind of model the property within the kind of as a property of the queue. And if you give it to our solver, it is going to say, yes, this property does not hold. And here is why. Here is for this particular input. If this particular input happens, then this property is going to be kind of violated. So remember the input, the way we model that input, where it is timed packet sequences. So we set multiple packet sequences that are entering the network at different points in time. And we made sure that we include a lot of details here, exactly what packets enter each location in the network at which point in time. So we thought that this level of detail is going to be important in our model because we wanted to see how different packet streams interact with each other. And kind of figure out, who ends up in the same queue together, how big the queue becomes. So for our model, this was something that seemed to be useful, but this is not necessarily helpful in the output. Because if you're trying to kind of figure out what went wrong, right, the specific detail of, what matters here is that the higher priority queues, F1 and F2, had some packets in them that ended up blocking F2. But it doesn't really matter that this one exactly got 3 packets in the first time step. It would have been completely okay if it got like 2 packets here and 1 packet here. It also doesn't matter if this one actually doesn't matter at all. It doesn't matter if this one received no packets in the second and the third time step. So this level of detail in the output, there's too much, there's a lot of information that is actually not going to be helpful to the operator to understand what the main problem is. So apart from that, another reason why this might not be an informative output is that it's kind of a very detailed single packet trace. If you're saying if packets enter the network exactly this way, then this problem is going to happen. So this could be a 1 in a billion packet trace, and the probability of this exact sequence happening in reality might be very, very low. And especially when it comes to performance, you might not care, right? Because you're operating a network, you want to provide performance, good performance most of the time. And if there's like a single packet sequence once in a billion that could cause some bad performance, maybe you don't really care about it. This is in contrast with functional correctness. If you're looking for a security bug, even if you find one execution trace that causes the problem, you're going to care and want to fix it. But when it comes to performance, you're always making trade-offs. You're saying I'm going to optimize for certain kind of workloads compared to others. So a single packet trace might not be, again, a helpful indicator of a problem. Right. So what did we decide to do instead? Instead, we said, how about we can output, instead of a single packet trace, a set of conditions on the input that could violate the property. So in this case, what that would look like is, if F1 or F2 have packets for X consecutive time steps, then F3 is going to get blocked. And I don't care exactly in what order F1 or F2's packets come in, if they come in a burst or one at a time, as long as for X consecutive time steps, they have some packets, the higher priority queues, then F3 is going to get blocked. And this is what we're calling a workload in this context. And the way we have defined it more formally is as a conjunction of constraints over the input packet streams to the network. And we think this is kind of a better and more informative output because it is representing a set of traces in a concise way. So it can be more informative. You kind of get a notion of, like my problem is that I have strict priority, so the higher priority queues are going to block the lower priority ones. And because it's representing a set of traces that can cause a problem, it can potentially be indicative of kind of a bigger problem. All right, so back to this picture. So what we had before was that we would give our formula that we don't have here, model and the negation of conjuncted with the negation of property to a model checker. And then it will give us either, yes, great, the property is always full, or a concrete packet trace that violates the property. Now we want to change that to actually return a workload such that every trace that is in that workload is going to violate the property. And the way we do that is through something called syntax-guided synthesis, which is kind of a well-known technique, again, in programming languages and formal methods community, where basically we use a grammar to define the space of possible workloads that we want to consider as answers to the user. Then we have a search algorithm that will basically pick a candidate workload and then try to figure out, do all the traces in this workload going to violate the property? So this question is something that our bounded model checker can answer, right? Because we're just saying, so this could actually check if these formulas are satisfiable or not. If the answer to this question is yes, then we're done. If it's not, yes, the bounded model checker is going to give some feedback to the search algorithm to try to pick a better candidate next time. All right, so I just want to go into a little bit of detail about this. And I just realized that some animation, once we turn this into PDF, might be missing. So I'm sorry that it's blocking some part of the screen. But the search algorithm, what the goal that it has is to find a workload, right, such that every trace in that workload is going to violate the property. So to start with, we just start with a workload that puts no constraints over the input. So it's kind of containing all possible packet traces to the network. And then we start making random adjustments to it until we find an answer. So remember that our workload is a conjunction of constraints. So the random adjustments that we make is either to add a random constraint, or remove one of the existing constraints at random, or pick one of the existing constraints at random and modify it again at random. And to kind of make sure that we converge faster to an answer, these adjustments are guided by a cost function. And I'll talk about a cost function after this. But we have a cost function that tries to capture how close we are to an actual answer. So if you make an adjustment to a candidate workload and it has a lower cost, we'll definitely try it next as our next candidate. If you modify it and it has a higher cost, then we still try it with some probability because we don't want to get stuck in local. So all this algorithm, again, this is not new. It's based on Metropolis Hastings MCMC, and this was inspired by prior work that used similar techniques to synthesize programs, that small programs or invariants, program invariants. But we did make several optimizations to make this fit our specific situation better. The cost function for sure, and also for the search, we added a bunch of things to skip local minima, like looking ahead, random restarts. Remember, every time that we pick a candidate, we're asking that solver to tell us if this is the, the verifier to tell us if this is the right workload or not. Those are expensive calls, so we made some optimizations to try to reduce them. And we don't try modification once at a time, we try multiple modifications at a time, and so on and so forth. Right. And because we seem to have time, I want to also dive a little bit into our cost function. So it's the cost function that is helping our search algorithm picking the next candidate better. So it's representing how close the candidate workload WL is to an answer. So this is how we've constructed our cost function. It is a linear combination of these two cost functions, cost of E and cost of S. So for this first component, right, the way we kind of approach that is what we want from kind of the workload, the candidate workload, is we want all the traces in that workload to violate the property. So to kind of get an estimate of does it actually happen or not, before we start the search, we create two sets of examples, G and B. So these are exact concrete traces that we generate before the search. There's no formulas like actual concrete packet traces. So the good set, the set G, is all the traces that violate the property. And the reason we call it good, it might be a little confusing, but it's because it's the ones that we're trying to find in the search. And we also create some traces that do not violate the property. So what we want as we're searching is for this candidate workload to move away from the bad set and have as much intersection with the good set as possible, right? So this is probably kind of further away from the answer because it contains, some traces that do not violate the property, and it contains no traces that violate the property, or no intersection with this set. And as we're kind of moving down, this workload is probably closer to a better. So that is our first cost function. We have this example traces, and every workload candidate that we have, we kind of compare this intersection with these two sets to kind of get a number on how good it is. And then we also want this workload to be broad and concise. Remember, one of the reasons we had for doing this in the first place was to try to find prominent problems. So the broader this workload is, the bigger set of traces it represents, the better. So the second part of our kind of cost function is kind of designed to favor simpler workloads, the one that have fewer constraints or constrain fewer queues or kind of have fewer time fragments. So what we do is that we kind of give higher weight to this at the beginning of the search. We just kind of find one good answer. And then as we find one good answer, or in an area that has some good answers, then, this one can kick in more and kind of give us a workload that is simpler. Right, so I'm going to skip this if you're interested. So generating the sets was not straightforward, especially for this good set. But if you're interested, I can talk more about that. And there's a lot more information in our paper that if you're interested, you can check out. I'd be happy to answer questions about it. All right, so all these pieces, going back to this picture, they put all these pieces together to kind of create, prototype them to create this tool called FPerf that stands for Formal Performance Analyzer. And we wanted to kind of see how well it does, so we applied it to kind of going back to our goal. We wanted to see if network operators can tell, this can help them tell if they have picked the right algorithm. So one set of algorithms we tried were packet scheduling algorithms. So as some sanity checks, we tried kind of simple schedulers like a priority scheduler and a round robin scheduler. A fair queuing scheduler, which is used in the Linux kernel. And these were kind of standalone schedulers on their own, so one queuing module. And then a composition of a bunch of schedulers that had about 11 queuing modules. And it was inspired from some prior work that was trying to reason about a composition of schedulers. So it does seem like, again, there's some animation that was lost here, but in terms of model size, just to give you a sense of how big these models in terms of variables and constraints get, it's like in the tens of thousands, and as like for the composition on the higher ends of tens of thousands. The search algorithm, it takes a couple of hundred rounds with the optimizations that we have done to try to find an answer. And the verifying workload, so this would be the part where we're asking our bounded model checker to analyze and kind of see if the formulas are satisfiable or unsatisfiable. So that actually does pretty well. On average, it takes, maybe a little bit less than a second for this more complicated example, which means all those optimizations that we did that I didn't get to talk about did pay off. And overall, we can synthesize these workloads as answers for the operators. So their questions in, let's say, like tens of minutes, 18.5 minutes is the kind of highest one here, which might sound a lot, but I do want to point out that our goal was just to show that this is tractable because when you go from reasoning about correctness to performance, a lot of complexity is added because you have to reason about things over time. You kind of have to do quantitative reasoning. So this was our first step to just show this is something that's tractable and we can try to optimize it further. We did try this also, so these were all just kind of standalone schedulers in a single device. We did try for a small network of connected devices to try to model them, formulate some properties that we're interested in. So this ended up being about twice larger than that composition example in terms of number of queuing modules and number of queues that it has, and we kind of observed similar trends. What I did want to point out before wrapping up is that once we try, so this is a small network, like real networks have, tens of thousands of devices, so this is just 5. as we try to kind of increase the size of the network, the analysis time, not surprisingly, increased exponentially, which means the next step that we've been trying is to do modular analysis. So can I just kind of reason about a subset of these queuing modules for some part of the network separately and another subset separately, and then combine the results further. All right, so I do want to go back to this question that we've been trying to answer. Can the help operators kind of answer this question of, if I deploy this particular algorithm or protocol, will the network ever experience good performance? So I think we've just started, right? So as I mentioned, there's many problems in terms of scalability that needs to be addressed, right? But one of the problems I'm going to focus on just for probably a minute or two is that still we require this kind of the model and the properties to be provided to these tools, which is something that is not fair to expect of a network operator to do. So what we have been also working on is to kind of create some higher level kind of domain specific CLI programs for people to just specify how packets are going to move between different queues in a network. So basically the processing part of a queuing module. So that already helps with, if we can kind of have a compiler to take those programs and create the logical formulas and feed it to this tool that we have, that already kind of makes it easier to use. But that also opens it up to trying other program analysis techniques like symbolic execution and other kind of optimizations that we may want to do. So that is something that we are also working on as next steps. And with that, I want to thank you for listening to the talk. I'm happy to take questions.
All right, thank you for a nice talk. Are there questions from the audience? If so, I will choose the other mic. Yeah, any questions? Okay, yeah, one second.
Thank you so much. And I have a couple of questions. The first thing is, you were modeling the network in a logical expression. So I just want to know what does the variable represents? I mean, what type of variables are there?
Right, so the type of variables so far, we're kind of using like integer and Boolean variables. So integer variables to represent whether there's a packet, like a Boolean variable to represent whether there's a packet or not. And then any attribute of that packet, like if it belongs to a certain traffic class, if there is some attribute you want to keep, it is accompanied with a finite number of integers. 2 was what we've tried in a lot of our use cases.
Okay, and another question is, are you prioritizing the packets? There is a prioritizing technique you are using.
Is prioritizing?
Are you prioritizing the packets when you are scheduling the packets? Hello.
Sorry.
That's okay. I think I heard your question. So I think the way I will what did I do? Let me go back here. Right. So each of these queues is a first in, first out, right? So then the Waving model that is a bunch of first in, first out queues, and the scheduling decisions are happening here. So this can do the priority, but for the packets in a single queue, there's no extra priority to say the packet at the end is going to kind of jump and jump, and each queue itself is first in, first out.
And last question, I mean, this, since you were using the logical expression, so you were using a solver. So is the solver is problem specific, or I mean, it's a general solver.
It's a great question. So I think this was as I mentioned, kind of starting point of is this going to work or not? So I think we picked kind of off the shelf, whatever off the shelf worked and tweaked. So in this case, we're using Z3, just off the shelf. Didn't even change any, like didn't optimize it a certain way. So we mostly optimized the encodings, not the software. As part of our kind of ongoing work that we're trying to optimize things for, I think we're trying to do some more domain-specific optimizations and yeah, but with this work, yes, it was the generic software.
That's it. Thank you so much.
Sure.
Any other questions? No? All right, let's thank Dr. Arashloo one more time.